Most amateur video is shot by hand, and the result can look remarkably shaky and hard to watch, such as this sequence I shot walking backwards. Such shots are often called tracking or dolly shots, and professionals will capture them using a camera mounted on a rail system, or a Steadicam. Most of us, however, have to make do with stabilization software, such as Shaker. Here we see that current software can successfully reduce camera shake, but the result still doesn't look like a motion a professional would capture. The camera still wanders around aimlessly. Here we see our result, which simulates a camera moving along a perfectly linear path with constant orientation. The feel is much more like a classic dolly shot. And that's the goal of our system, to take a normal handheld video and automatically convert it to a video that looks like it was captured along a directed camera path, such as a line, a parabola, or any 3D camera motion that is reasonably close to the original. Almost all video stabilization algorithms operate in 2D. Here we show our implementation of 2D stabilization on two sequences. This method tracks a bunch of points, fits a 2D motion model, and then low-pass filters that motion model to create an output. This approach can be very successful in damping shake, but since it has no 3D knowledge of the camera motion, it's not powerful enough to simulate a directed camera path. 3D video stabilization is more powerful. It tries to simulate what the camera would have seen from a 3D output camera path. Unfortunately, current image-based rendering techniques can't handle scene motion, so you get ghosting, as you see here. Our approach begins similarly to 3D stabilization. We use Voodoo, a publicly available structure for motion system, to reconstruct the original 3D camera motion and a cloud of 3D scene points. Then we fit an idealized camera motion to the original, such as a line, a parabola, or just a low-pass filtered version of the original 3D trajectory. Then we try to simulate what the camera would have seen from this new camera path. However, in order to preserve scene motions, we add the constraint that each output frame is a warp of a single input frame at the same moment in time. This implies that we must simulate an accurate shift in viewpoint using only the content of one image, which is of course impossible. However, we've found that for the purposes of video stabilization, we can fake it with a carefully designed content-preserving warp. For each moment in time, we can project the reconstructed 3D scene points to both the input and output frames. This produces a set of sparse displacements, from the red points to the green points, for each video frame that will guide our warping method. We could just fit a full-frame warp to this set of displacements, such as a homography in this example. Notice, however, that the buildings on the left wobble and tilt. This type of warp isn't flexible enough to model motion through a general 3D scene. For this other sequence, we see the buildings and statues shear to the right, and then to the left. Instead, we discretize a spatially varying warp over a quad mesh that tries to preserve local shape within the scene and follow the sparse displacements. The result for these two sequences is now much better. In this visualization, we spiral the viewpoint away from its original for one moment in time. It's pretty clear that our method does not produce an accurate novel view interpolation. However, if we play it again and pause it now and then, each frame looks pretty reasonable until the camera gets too far away. Note that we only ever see this moment in time for one frame in the output. This is really the key insight of our method. For the purposes of video stabilization, we can fake small viewpoint shifts with a content-preserving warp, even though the result is not physically accurate. Finally, along with the linear camera paths already shown, we now give an example of a parabolic path and a path created by simply low-pass filtering the 3D input motion. We now show some more results and comparisons. This first example was shot with a camera with a rolling shutter, which is very challenging for current 2D stabilization software. Our method performs better on this sequence. We now show more results, as well as comparisons to the results of existing methods and commercial software.